So good morning, welcome to Krishna's classroom. We considered the concept of orthogonal projections in our previous lecture. Now, in this talk, we explore some of the characterizing features of a orthogonal projection. So essentially orthogonality. Projections we have already characterized earlier. Okay. So let us set up the ground. Now let X be a finite dimensional inner product space. With the dimension n say. Let M be a subspace of X of dimension M, say. Now what we have is this 0 less than or equal to M less than or equal to N. The extreme possibilities, namely M equal to 0 and M equal to N. These are the extreme cases. These are the extreme cases, and they are also trivial in some sense. You will see that all projections to M along M perp or all projections to M are orthogonal projections. I mean, that's not difficult to see in these extreme cases. So they are somewhat trivial. Now let us consider the following. So without loss of generality, we assume we take the case the non-trivial situation. Now we have a breakup of X. X is now a direct sum of M and M perp, where M perp consists of all those X belonging to X such that X is orthogonal to Y for every Y belonging to . Now for every M there is an M perp because we are in an inner product space. In the general case that we considered earlier where we didn't have an inner product, still you have M and a complementary subspace N But we didn't have anything to talk about orthogonality. We didn't have the machinery to talk about orthogonality in those situations. Then of course, let's recall for x, z belonging to x, we have uniquely determined vectors x belonging to M and y belonging to N, M pair, such that z equal to x plus y, and this allows us to define what is called the projection operator on M along M pair. We define E from X by Ez is defined for then range of E equal to M and null space of E equal to M pair. Then we say that E is an orthogonal projection. That means E is a projection on M along the space M pair which is orthogonal to M. That's the meaning. Okay? And you see that range of E and null space of E have the property that if you pick a vector from Re and if you pick a vector from Ne, then they are orthogonal to each other. So we are completely exploiting the advantage or the presence of an inner product and also the concept of orthogonal vectors to introduce a new class of projections, namely orthogonal projections. Then E is called an orthogonal projection. X with range of E and null space of E okay. So we have seen that, E is a projection, that is no difficult. This definition makes E a projection because we note that E is equal to E square. Because E is now a projection and you can directly verify that E is equal to E square. Therefore, projections here the additional property that you have is that E is an orthogonal projection. That is because you have the range and the domain, the range of E and the null space of E are mutually orthogonal. Okay. So our question is this: is it possible to characterize the in terms of the properties of this is the question that we explore. We give some different characterizations. Okay, so let us start with the main results. Okay, so let us see, we already know that if E is equal to E square, if E is a linear transformation on X and E is equal to E square, then it's a projection. So when is it an orthogonal projection? This is the question. On X you have an inner product. Okay, so we have the following result. So you need some additional properties to characterize this, because what you have is E is equal to E square is already a characterization of a projection. But there are projections for which the range space and the null space are not mutually orthogonal. So such a scenario exists. Okay, therefore what additional feature essentially assures you that they are orthogonal? This is the question that you are exploring. Okay, so we have the following result. E belonging to is an orthogonal projection if and only if E square and its adjoint operator, that is E is self-adjoint. See, if E is self-adjoint and projection, then it's an orthogonal projection. So that's the theorem. So this is a necessary and sufficient condition. So let us mark this theorem out. This is one of the characterizations that you have. Okay, let us try to prove this. See, what you have is that E equal to E square makes it a projection. Then what more you need to make it an orthogonal projection? This is the question. Or what additional condition when added to E equal to E square will make it a orthogonal projection? So it's a nice characterization theorem. Now we will just make some remark before we prove the theorem. Let us consider X to be equal to R2. Okay. Now we take M to be equal to the axis, the x-axis, and N to be, or I can write it this way, the set of all x belonging to R. This can be equally well described as all those xy for which y equal to 0. Okay. Now we take N to be equal to the set of all xy such that y is equal to minus x. Then you can check that M equal to this is quite easy to check. I leave it you to verify that. Therefore, and you also have, okay, so now define, therefore you have considered let us try to understand this problem pictorially. So what is that you have? This is your standard R2 with the standard basis. Now what you have is this. See, one of the spaces that we consider is okay. One of the spaces that we consider, M is taken as this space. So this is your M. This is the x-axis. And N you take as the following space, namely this is your M and N are not orthogonal with the conventional inner product that you have. Okay. So M and N are not orthogonal. So let us now explore. Suppose you take a vector AB described in terms of the standard basis. Okay. And look at its projection on M along N. So what do you do? This is the vector that you are having, and now you are projecting it to the x-axis along the y-axis. So what do? You complete the parallelogram with sides on this. This is the usual technique that you have. Therefore, you see that the projection, what are the coordinates of this point? So AB you take as an arbitrary point. Then the coordinates of this point are, you see that you can easily find out. This is the line. This is the line x plus y equal to. It's parallel to it, and now we are trying to find out the intersection of this with the x-axis. That is, you put y equal to 0, then that will give you the point of intersection is going to be A plus B comma 0. So AB gets projected Now let us look at the matrix representation in terms of the standard basis. So the matrix representation of E in terms of the standard basis E1, E2 will be given by the map that carries AB to A plus B. So you can easily see that this is the following. Okay. So you get 1, 1, 0, 0. Easily check that if you take AB, then it gets mapped into A plus B, 0. Okay. So clearly you can check that that is easy to check. You can actually do the computation. Okay. But now look at this matrix. This matrix, now you see that E, because it's in the usual inner product. See, you take E star or take the matrix representation of E star. This is given by the transpose conjugate of this matrix, which will be 1, 1, 0. Then you see that E not equal to E star, which implies the operator E is not equal to E star. So E is not self-adjoint. Okay. But what you have is that M is not orthogonal to not orthogonal to N. That's the example. Okay. Right. So this example is a pointer to that, the fact that if this is so, then the adjoint cannot be equal to the original operator. Okay. Right? That is, E cannot be self-adjoint if you have in this particular example. So you are asking the question, is E equal to E star whenever it's an orthogonal projection? Little bit of work would show you that this is indeed so. Okay, it's not difficult to work this out. You can, now what you can do is you can choose, say, so explore the following. The same example you can explore with mutually orthogonal subspaces. Okay. So let us explore this. Now consider the example. to M equal to 0, and N you take as xy okay. So what you have is the picture that emerges is this. This is the standard E1 and E2, and this is the space spanned by E1, this is the space spanned by E2. Now we will mark the two subspaces, and M is as before, this is M, and N is taken as this one. This is something orthogonal to this. Now let us take some arbitrary AB. I mean, although I have marked it in the first quadrant, it doesn't matter. It's any quadrant, it is true. Now we are trying to work out. So this is the line x plus x minus y equal to 0, and this is of course say x plus zero. Now we want to work out the projection of AB onto M along N. So N is orthogonal to that is done. Now let us work out the projections. Okay, right. So what do you have? You have this, you take the projections. Find out the coordinates of this point. So we are trying to find out what is the projection of AB onto M. Okay. So let us work this out. So what you are doing is you are trying to find out the line, the equation of this line. The equation of this line is x Now what we are doing is we are going to project AB to this, so we want to find out the coordinates of this point. Okay, so what you do, you solve these two equations. Solve the equations. So you have two equations, namely x minus y okay. Now what we are doing is we are going to write down the projection onto this. So this is the projection that you have. This is your operator E. Okay. So what you have is you are taking this line has equation y equal to a plus b, like before. Now we work out the coordinates of this point. That is the point to which AB is projected. So you have to find out solve these two equations. And then so you get x is equal to, see, this gives x equal to y, or you get x is equal to by 2. and then y is also equal to so this point has coordinates a plus b by 2 so what is the transformation? So E carries this point. Let us write down the matrix of this. The standard representation is going to be 1 by 2, 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 1 by 2. Now look at the matrix of E star. Is the transpose conjugate of this. This is again equal to so in this case E equal to so in the case where you have orthogonality, now you can, in fact I have taken a very simple scenario with a well chosen, for simplicity, well chosen M and N. But you can choose an arbitrary M, that is AX plus this. So exercise. Cos alpha square plus beta square not equal to 0. Okay, with this condition. So we will put it here itself. You know that this is a proper one-dimensional subspace of N. Now choose N equal to M bar. So compute M bar. Let be the projection on M bar. Show that Easter. So that you do the computation, the general scenario. I have taken a very specific case. Okay, so you will convince that E equal to E star seems to be something that comes out at least in R2 with the general choice of a subspace M and its orthogonal complement as N and then computation. So I leave the computation to you. So fine, this is a very simple scenario which I have worked out. Okay, so what do we do? Now we want to, so what we guess at this stage is this. Suppose E is a projection, namely E equal to E square is satisfied, that it is idempotent. And if it is an orthogonal projection, then we expect E equal to E star. Conversely, suppose E equal to E star in addition to the fact that it is a projection, then E is an orthogonal projection. So let us prove this theorem now. Now we go to the proof of this theorem. So let me keep this theorem on the board, and then let us now write down the proof. So let me take out this complete remark. Okay, so in the problem. Now let me write down the proof of this theorem. So one of the things that you observe at this stage is that, okay, let us make some assumption. Okay, suppose we assume, so we prove this. Suppose then claim P star. These are the things that we, so this is a supposition that we make. So that's quite simple. So if you have, you see this E is an orthogonal projection, means that since E is a projection, on the range of E along null space of E, we have because every projection is characterized by the condition that E is equal to E square, so that follows from that. Now all that we need prove is that E is equal to E star. So we now prove that E star. So what we do is we make a choice of the basis for M, and then we have, what we have is this, that we are having, say, range of E M denote this, and dimension of M. Okay. So what we have is that since E is projection, is orthogonal to null space of E, and x is equal to okay. So we use this. So let us put this star here because that shows that there is only zero element between. So they are independent, linearly independent subspaces. Therefore, let us now write be an orthonormal M which is equal to range of E. Now choose a such, because you are in inner product space, it exists because they themselves are inner product spaces. So what you get, say so you know that the dimension of any or the complementary subspace of M is n minus m. Therefore, let us designate the orthonormal basis or n orthonormal basis that we choose for n as xm plus 1 etc. xn. Then the first observation is that so we have an orthonormal basis for x constructed out of the orthonormal basis chosen for the range of E and the null space of E. So what do you have? The consequence is that the inner product of xi with xj this property we have. So we are going to make use of that. Now you see that what is E star? So E star is defined by which exists this property defines, determines E star. Then E star is in Lx. Okay. Now, in particular, see, all that you need is what about Exi? We have Exi equal to Xi for I belonging to and Exi equal to 0 this property you have. This defines actually the linear transformation E, okay, because it is defined on a basis. Now what we want to show is that we claim E star sufficient to show that E star of and for I M and E star of N, so that So what we need to prove is this result. So if we prove this, then E equal to E star. So our attempt would be to prove this result. Okay. So let us make some observations. Make some observations. The observations are the following. So we start computing E star of xi. Okay. So we have, let us make some results which really go into making this. So we note the following. x1 E star x1 equal to essentially Ex1 x1, and this is equal to x1 x1 Similarly, you compute this. Zero. Here we go through the same steps. You will get inner product of x2 with this one, and so on. We get xn zero. So this we note. What does it say? It says E star of x1. When you take the inner product with x1, you get 1, otherwise you get 0. Okay. Similarly, you have zero, x2 equal to 0, equal to 0. This is what you get. That gives you information about E star x2. We want information about all this, E star of xi. Now you see that this you can continue, and what you get is that inner product of xm okay. And xm E star of equal to 1. Further, xi E star of equal to 0 for I equal to So you get information about E star of Xn. So I think I made a mistake. It is 1 here. Right. So that is there. And the next thing that you can easily prove is this: Xi E star of Xj equal to 0 for I j belonging to this is also very easy to verify. Okay. So having got that, now you can find out what E star of Xi is. So let us look at X1. Suppose E star of Xi equal to Y which is equal to C1 X1 plus, where C1, C2, etc., Cn are uniquely determined and it is expressed in terms of this. Therefore, what do we have? We look at the first result. Therefore, you have 1 equal to which is equal to E star of X1. You write Y. Y is one to n. Now this you see is nothing but C1 conjugate, because of we have used all the properties there. It's easy to compute. That is the orthonormality of these vectors we work with. Right. Now what do we have? Similarly, you have 0 equal to which gives you Cj conjugate, okay, which implies Cj equal to 0 for j that implies, therefore what you get E star of X1 equal to X1. So that is what you get, because E star of X1 equal to Y, Y becomes X1. A similar analysis using all these results, you can prove E star of xi for I equal to, which we have already proved, m, and E star of equal to 0 for I equal to therefore you see that exactly, so this shows that E star is equal to, okay, so which in turn implies E star equal to E. This is a proof which does not go back to the definition of what you call dual operator and etc. etc. I wanted to avoid that because that needs recalling a lot of machinery which is not in front of you. Okay, but that there is another way of doing it. You can look into Halmos how you prove this. It's recalling an earlier theorem and then identifying A prime with A star and so on with this result. Therefore, let me now, so we have proved one part of it. Okay, right? Now what do we want? So the next part is proving the following. What is the next part of the theorem? The next part of the theorem says that you want to prove if E is an operator, if, so we assume we are trying to prove in this direction. Then claim projection. So it is sufficient to verify that the range of E is orthogonal to the null space of E. So we have M equal to range of E null space of E, and E is a projection, of course. E equal to E square, therefore E is a projection. By the general theorem on projections, E square on M this we know from the general theory of projections. Okay, now it is sufficient to show that so let x and y are in M. Then we have the inner product of x with y. If we show that this is, since they are arbitrarily chosen, if we can show that this is equal to 0, then you are done. Okay, so this is equal to, see, x belongs to M, therefore I can write this as EXY. And that's equal to what? X E star is the joint of E. But we are given that E star equal to E. Therefore, this is X EY. But then you know that Y is in N and EY equal to 0. Therefore, this is X 0. Therefore, that is N is equal to, so what we have is that is an orthogonal projection. So that completes the proof. Okay, so that's one characterization that you have. Now we make a, so we'll just make a corollary. If E star then E is a positive definite operator. So that is easy to prove. We just check the definition. Now you see that, work out this Ex, whether this is greater than or equal to 0 for every x. For any x, Exx is equal to, by definition, because of the property that it is E is a projection. Now this is equal to Ex E star okay, E star x, and this is equal to Ex square, which is certainly greater than or equal to 0. Therefore, we have Now we make one more observation. If the projection is not an orthogonal projection, then we can actually show that there exist some vectors for which norm of Ex is greater than norm of X. Okay, let us explore this problem. Yeah. So you can make this observation. See, Ex and Ex belongs to range of E, and I minus E of X belongs to the null space of E. Okay, this is a general result that you have. So if E is Ex is orthogonal to I minus Ex. Now that's very easy to see. Therefore, and this you can write as this can be written in this way. Now use this orthogonality. Okay, therefore, and linearity of E, and then look at the properties of the inner product and so on. Yeah, fine. So this would give you that's easy to compute. Just use this orthogonality property. Okay. Therefore, what do you get? Therefore, it follows that if I drop this, that is norm of so whenever E is an orthogonal projection, then this is what follows. That's very easy to verify. But we also make an observation here that if E is not an orthogonal projection, then you may have problems. And this may not be true. So let us take up the case where E is a projection but not an orthogonal projection. So let us look at an example. So consider the example. As before we look at some examples, so get some insight and then ask some bold questions. If E is not an orthogonal projection, then the observation may not be true. This is what we want to observe. So consider the example. You take x equal to R2, then we take M to be equal to that is the x-axis. Then N you take as x equal to y. So once again we go back to our old picture. This is your R2. So spanned by E1 and E2. And then you have M, of course, you take as this one. This is your M. And N is this is your M. So this is your M. This is your M. So this is x plus y equal to I take N as x equal to minus y. Okay, so this is your N. So this is x plus y equal to, this is y equal to 0. Now let us take the projection of a vector. So I want to show that there is some vector when projected onto M, that is Ex. Okay, right. So take this one. Take any AB. Let us take 1, 1. The vector 1, 1. and project it let me, all that I want us to show that there is a vector with this property. So let me take 1, 2. It's 1, this is 2. Let me take the vector 1, 2 and find its projection onto the space. What is that going to be? You draw a line parallel to this and you will see that the projection is essentially 3, 0, the vector 3, 0. So Ex equal to and norm of x equal to square plus 2 square phi norm of Ex square equal to 9. Therefore, in this case, that norm of greater than so we have seen an example where you are talking about an orthogonal, a non-orthogonal projection, where this particular inequality may not be true. Okay, so our question is this. So the question is this: is the inequality for an orthogonal projection, for a projection E, a characterization for E as a orthogonal projection. So does this become a characterizing feature? This is true for every x. Suppose E is a projection and norm of x is greater than or equal to norm of Ex for every x. Does it imply that E is an orthogonal projection? So let us prove this theorem now. So that's our next characterization. Okay, let me do that now. So one should try to associate with or have a good feeling from examples before one starts with a theorem. And that gives you suggests you the way in which these ideas have emerged. So let me do that. Next characterization theorem we are writing. An orthogonal projection if and only if E equal to E square and norm of that's the next characterization. Of course, we have already proved this, that, okay, assume E is a E is an orthogonal projection. See, we are going to prove this. Then we have and Ex orthogonal to E being an orthogonal projection this we have already verified. We have consequently norm of as we have already proved. Okay, so that we have already done in the corollary. Now we want to prove in the reverse direction. That means assume, what are the assumptions that we make? E square and then what we claim is this. Projection. So what do we do? First of all, E is a projection. E is a projection. E square. Okay. Okay, so let write M be equal to then M perp equal to N, or equivalently N perp okay, so it is what is required is to prove this. Sufficient to prove that so suppose x belongs to n perp which is equal to n. Then x belongs to n, because you can show that Ey equal to 0. Because E square is given, so see E square equal to E, and therefore you get this is equal to 0. Hence Ex equal to x plus y with equal to 0, with xy equal to 0. That's easy to verify. Hence, you have norm of x square is, it is given that this is greater than or equal to norm of ex square, which is equal to norm of x square norm of x square plus norm of y square. Okay, and this is clearly greater than or equal to, what does this mean? See, this particular inequality tells you that norm of x square is greater than or equal to norm of x square, so all this is squeezed in between, and therefore what you have, this implies equal to 0, norm of y equal to 0, which implies Ex equal to x. That is, x belongs to M. So we have shows that y equal to 0, therefore Ex equal to x, which implies it started with an x belonging to M. So that what we have is that n perp is contained in M. Conversely, so we want to show that actually n perp is equal to M. Conversely, if M, the range of E, then Ez equal to Z, right? Where x belongs to M, which is equal to n perp, and then Z is equal to Ez, which is equal to Ey, and this is equal to Ex, which is equal to x. Therefore, which implies belongs to M. Z belongs to M. Therefore, what we get is that M is contained in perp. Hence, together, these two results together M is equal to n perp. Okay, so that completes the proof of this. That is projection. So I think I'll stop here. Continue with it possibly tomorrow. Thank you very much.